Hello everyone, and thank you for stopping by and watching my poster. Our main goal for this project is to advance biomedical science with quantum computing and quantum machine intelligence. So let's get started. In the first work, we introduce ANN, a quantum neural network for sequential data analysis. First, we introduce parameter sharing into the quantum asset design and to perform time encoding over the input. And then a continued relaxation based on softmax function is introduced to aggregate information and to form final prediction. As a result, we can provide highly accurate Bayesian classifier for regression problem. And our model knowledge can be transferred across dataset to improve the model performance on small data scenario. If you want to discuss more about the model, please visit me at poster 47 at the conference. In the second work, we aim to generalize quantum neural network using triplet of probability theory, including sample space, event space, and probability measurement. Let us show one example here. Suppose we toss a record 3 times and it comes head, tail, and head. We can present the signal as 1, 0, and 1 in the sample space. Then we can construct any random process, for example, by summing over the generated signal. We present the random process by working agent in the event space. If we do the experiment multiple times, we will see the overlap in working agents. For example, here we do 3 times and we can see agents from experiment 1 and 2 are overlapped. We can further provide the instruction for the agent to distinguish them. For example, we can instruct the agent move 1 unit up on the orthogonal vector space in purple. This will produce count statistic or probability measurement. After many experiments, we can form a computational blocks. We name these blocks probabilistic information block. It is not that the purple vector space will provide full information about probability measurement. A natural question is that what information we can capture on the orange vector space? With this motivation, we introduce the Duality game to simulate probabilistic information blocks. It is inspired by the Heisenberg uncertainty picture. It is claimed that if a particle is well-defined in position, it will ill-defined in momentum, and vice versa. Our game setting includes 2 players, realist and orthodox, trying to observe the information blocks. Their vision will completely orthogonal. Realists will fully observe the positions or purple vector space. Orthodox will fully observe momentum or orange vector space. To implement the duality game, we introduce triplet data field, a quantum neural network using only 3 quantum kernels. First, over the half evolution of qubit, presented by RSG rotation, 2 players will manipulate the quantum state and to maximize their rewards. Realists can control Rx rotation. Orthodox can manipulate Ry rotation. The game condition is that orthodox wins when quantum state is kept 0 or the player minimize the distance from their vision to the quantum state. Realists win when orthodox lose or quantum state is 1. We present the quantum ansatz circuit for the duality game in the right panel. Here's some interesting properties of our triplet data field. Using 1 qubit, we have the dynamic behave like positions. The agent start with value A, will end with value minus A. Using 2 qubits, it will behave like probability functions. The value is capped between 0 and 1. And using 3 qubits, it is hypothesized as a energy function, which is proportionate to momentum. And interestingly, the dynamics is periodical as we increasing the number of qubits. Even qubit system behave like probability measurement, and odd qubit system behave like energy function. In the first result, we aim to approximate von Bartholomew growth with presence of noise. It is shown that our model can well approximate the true dynamics under the 2 criteria. And it is noted that the model performance remains nearly the same as the noise increasing. 2 more use cases will be presented at our poster, including COVID-19 modeling and tumor burden modeling. So please visit our poster at 47 to discuss more. In the last work, we aim to unleash the full power of quantum machine learning to tackle the most challenging problem in cancer research, which is patient-specific biomarker identifications. Human genomes will induce a very massive search space for this problem, and we will use quantum neural network to tackle this. Under relevance and redundant criteria, we can identify crucial marker for some target pathway, and we will use statistical and biological background to enhance the analysis. And here we investigate well-known driver in pancreatic cancer, including KRAS, GNAS, TP53, BRAF, and RNF43. And then we're re-engineering ANN using capture-inspired mechanism to enhance its explainability. We present each target pathway here is RAS and GNAS within one neural capture. And then we train the model to learn the mutational signal from the using conventional entropy loss. Using the identified marker set and its learned signaling indicator, we can construct highly accurate deep learning survival model. In average, we can reach 0.7 in C-index using 3 variants of the model. And then we can further improve the robustness by ensemble learning, as shown here by 10 classifier. Besides, we can explain the risk for each patient by neural signal that present by the target genes, for example, GNAS and RAS. And in the final contributions, we introduce the FISHBONE plot for patient comparisons. Clinicians and doctors can use the neural descriptors here to compare patients, and we can further compare the neural signal for each genes across multiple patients. So in summary, we have introduced a new set of quantum machine algorithms that show practical usage in biomedical science. So don't hesitate to visit us at poster 47 for more discussion. And thank you.